Salam and hi everyone. Okay, today we are going to learn about series resonance circuit and parallel resonance circuit. So the outlines of this chapter, the first one we will look into the series RLC circuit, and then we will learn how to calculate the quality factor Q, the bandwidth B, and the last one we will look into the parallel RLC circuit. So what is resonance circuit? Okay, resonance is a condition in an RLC circuit in which the capacitive and inductive reactance are equal in magnitude. It occurs in a circuit with capacitor and inductor because the collapsing magnetic field of the inductor generates an electric current in its windings that charge the capacitor. Then, this discharging capacitor provides an electric current that builds the magnetic field in inductor. Once the circuit is charged, the oscillation is self-sustaining. So no external periodic driving action needed. So it will cause the oscillation of stored energy from one to another. The resonance circuits are useful for constructing filters, and it is also used in many applications such as selecting the desired stations in radio and also TV receivers. Okay, next, series RLC circuit. A simple series resonance circuit consists of an AC source, inductor, capacitor, resistor in series connection. Okay, according to this figure, the input impedance is the sum of the resistance and the reactance. So, the impedance of the circuit is equal to R plus J omega L plus 1 over J omega C. And then we rearrange this equation, we put the J outside of the bracket. So we get like this. So actually resonance occurs when the imaginary part of this transfer function is equal to 0. So meaning that when the resonance occurs, this value is equal to 0. At resonance, the imaginary part of this transfer function is equal to 0. So omega L is equal to 1 over omega C. So since the frequency for both reactants is same, so we can change the frequency to resonant frequency. So 1 omega naught C. So we solve for the omega naught in order to find the resonant frequency equal to 1. So omega naught squared is equal to 1 over LC. Therefore, omega naught is equal to 1 over LC. From the previous derivation, the resonant frequency omega naught is equal to 1 over LC in radian per second. Okay, note that at resonance, the impedance is purely resistive. Thus, Z is equal to R, since the imaginary part of the transfer function is equal to 0. In other words, the LC series combination acts like a short circuit, and the entire voltage is across R. Second, the voltage Vs and the current I are in phase, so the power factor is unity. Third, the magnitude of the transfer function is minimum. Fourth, the inductor voltage and capacitor voltage can be much more than the source voltage. Refer to this graph the highest power dissipate occurs at resonance when I equal to Vm over R. So the highest power dissipate is equal to 1 over 2 times with Vm square over R. Okay, at certain frequencies, for example here, we have omega 1 and omega 2. The dissipate power is half of the maximum value. So, P omega 1 is equal with P omega 2 is equal to Vm square over 4R. Omega 1 and omega 2 in the previous graph are called as half-power frequencies. So these are the equations to calculate the half-power frequencies for omega 1 and omega 2. So in order to calculate the bandwidth, we use this equation. B is equal to omega 2 minus omega 1. Sharpness of the resonance in a resonance circuit is measured quantitatively by the quality factor Q. So this is the equation to calculate the value of Q. The quality factor of a resonance circuit is the ratio of its resonant frequency to its bandwidth. The selectivity of an RLC circuit is the ability of the circuit to respond to a certain frequency and discriminate against all other frequencies. The higher the value of Q, the more selective the circuit, but the smaller the bandwidth. If the band of the frequencies to be selected or rejected is narrow, then the quality factor Q of the resonance circuit must be high. A resonance circuit is designed to operate at or nearly its resonant frequency. The resonance circuits will have Q value greater than 10. It is called high Q circuits and often used in communication networks. So for high Q circuits, the half-power frequencies, which are omega 1 and omega 2, are symmetrically around the resonant frequency and can be as approximate as shown in this equation. We will continue with example 1. Okay, given a series RLC circuit here, okay, so the value of R is equal to 2 ohm, L is 1 millihenry, C is 0.4 microfarad. So the first question, you need to find the resonant frequency and the half power frequencies. Second, you need to calculate the quality factor, which is Q, and the bandwidth B. Determine the amplitude of the current at omega naught, omega 1 and omega 2. So for the first one, in order to calculate the resonant frequency omega naught, so using the previous equation given, so omega naught is equal to 1 over CLC, which is equal to 50k radian per second. Okay, so this one quite simple. And B, calculate the quality factor Q and the bandwidth B. So the equation to calculate the Q is equal to omega naught times VR over R. So it is equal to 25. So for the bandwidth, B equal to R over L, which is equal to 2000 radian per second. Okay, since the value of the Q that we get is 25, which is greater than 10, so we use these equations to calculate the half power frequencies, which is omega 1 and omega 2. So omega 1 equal to omega naught minus B over 2 equal to 49k radian per second. So for the second one, which is omega 2 equal to omega naught plus b over 2 equal to 51k radian per second. So the next, you have to calculate the amplitude of current at omega naught, omega 1 and omega 2. So at omega naught, I is equal to V over R. Okay, so V is given in the circuit, which is 20 volt, and R is 2. So the current at resonant frequency is equal to 10 ampere. Okay, at the half power frequencies, which is omega 1 and omega 2, I is equal to Vm divided by Z2 times R. So we get 7.071 ampere. Okay, so this is one example of a series RLC circuit or series resonance circuit. So for this exercise, okay, using the steps explained before this, so you have to calculate the value of C, but the given quality factor is 50, and you have to find the omega 1, omega 2 and also B, and then determine the average power at omega naught, omega 1 and omega 2. So given the value of Vm is 100 volt. So you try to do this one, and then you compare your answer with the answer given here.